Um, Thanks so much for taking the time to join us for the this webinar. Today we'll be doing the BEL SOURCERER product workshop, and Kyle Morgan will introduce SOURCERER and present a hands-on demonstration of the software. During this product workshop, feel free to unmute yourself and ask questions as we go along. Kyle is happy to take questions during the presentation. So unlike some of our other webinars where we ask to hold it to the end, we think it makes more sense for this product workshop to ask questions as we go along. So if something comes up, if you have any questions, if something doesn't make sense, go ahead and unmute yourself. And I haven't enabled that, I believe. So yeah, we'll just take questions as we go along. Okay, so I am going to introduce Kyle Morgan. He's our BEL scientist and kind of our SOURCERER expert. So Kyle, thank you so much for doing this today. And I'll go ahead and turn it over to you.
All righty, thank you. All right, let me get some screens set up real quick. Okay, so just like Corin said, this is a workshop. This is not just like me talk, you listen. Get out of this what you would like. Feel free to interrupt me at any time. This is straight up just a workshop to show you SOURCERER, show you some ins and outs of it, give you some example data that I'm going to do some source estimation on. So if you have any questions, just pipe up. But before I delve into some of the kind of front end data organization stuff, I'm going to start by talking about some of the Atlas models that are inside of SOURCERER. So SOURCERER is a source estimation software. It utilizes Atlas models for now. There are no support for individual head models for doing source estimation just yet. That's coming in a future release. But these Atlas head models are pretty well constructed. So some things about them is we have 4 atlases inside of the first release of SOURCERER. There are 3 pediatric atlases, and then there's 1 adult atlas. So you can kind of choose the age range you are doing source estimation on. And we have kind of an age-matched atlas for each one of those age ranges. And some things about them, the atlases themselves are constructed of an average brain. And that's what we mean by atlas, is that the brain that we're using for source estimation is an average of many subjects or volunteers inside of the different age groups. So for example, here I have the adult atlas. This atlas is from MNI, and it's for, I believe, subjects that were over 18 years age, and there's about 100 average brains here. And then we have an atlas for the age range of 0 to 2, and then 2 to 8, and then 8 to 18. The atlas for 0 to 2 uses a brain from the University of North Carolina. They had a cohort of very young children from the ages of 0 to 2 getting scans at 0, 1, and 2 years old, and then kind of average them all together. And then the 2 to 8 and 8 to 18 use the age-matched atlases from MNI. And so the way that we constructed this atlas, let me see if I can remove some of this tissue here to give you an idea of what's underneath the hood here. So for each one of these atlases, what we did is we took that average brain and we warped it inside of the geometry of an individual subject who kind of closely matched some morphometric parameters for their age range. For this particular subject here, we have the MNI adult brain. You can kind of see it looks a little smooth from it being an average. And it was warped inside of an adult that had a full head CT image to image the bones, and then a full head MRI to image all the soft tissue and get a reference for the scalp. And this particular subject, we tried to match things like average head circumference, skull thickness, things like that, so that we're not just arbitrarily picking some random person off the street that has these two scans and warping a brain inside of it. These subjects that were used kind of as our templates were carefully matched according to some morphometric criteria. And the same goes for 0 to 2, 2 to 8, and 8 to 18. Those age nodes, there's a couple studies that I could show or share if anyone's interested in that, that those age ranges are kind of points in development where the brain is significantly different enough to where it warrants its own age node, if that makes sense. So from 0 to 2, not including neonates, from 0 to 2, the brain looks, roughly okay to where you can use an average brain across there. And then 2 to 8 looks different enough from 0 to 2 that it kind of warrants its own little brain. And then 8 to 18, same thing. So just know that these atlases were pretty carefully constructed. These differ. Some things that make it unique is that they are using average brains. Some other source estimation softwares that are out there use things like Colin 27, which is definitely not an average brain. It's an average of a single person's head. They had like 27 plus MRI scans averaged all together. These are things that kind of set us apart. Can I set browser full screen? Yeah, let me do that. Okay. So something else that we did when we constructed these atlases is the sensor positions on these atlases are averages, just like the brain. So the sensor positions are an average of, in this particular case, a 256 EGI net co-registered to the scalp. And then each one of these atlases has triples dipoles for source estimation. All right, close this down. So inside of SOURCERER, and I'm kind of getting ahead of myself here. I'm just trying to give you kind of a brief overview of what is in SOURCERER before I actually show you how to use it. SOURCERER includes kind of an array of different source estimation algorithms. So inverse algorithms, we have S-Loretta and Loretta, which are kind of the standard players in inverse solutions. And then we have Bayesian prior and spectral data. Spectral is special, that is spectral analysis. But I'll talk about Bayesian priors just a little bit. Bayesian priors is something that's unique to SOURCERER. We actually have a paper that I can share with people that our colleague Mariano wrote, I think it was just last year. But Bayesian sparse priors is a more focal solution than S-Loretta. It uses a large combination of prior assumptions, which kind of sets it apart from S-Loretta. And in Mariano's paper, what he showed with individual head models, which kind of is different from just using our atlases here, he used individual head models with from patients with epilepsy and used some spike localization data to show that MSP, or multiple sparse priors, is as accurate as Loretta against a ground truth, comparing it to a resected area of those patients with epilepsy. However, MSP was a lot more focal than those other solutions. So it kind of warranted itself being inside of our program, just given the fact that it is as accurate, if not more accurate from some experiments that I'm running now, than S-Loretta and Loretta, but it is very focal. So I can actually see if I can enter this into chat. Either way, at the end, I'll have Corin or myself share that paper. But if you have questions about MSP or that algorithm itself, you can read Mariano's paper in good detail. It delves into the weeds a lot more than I think that I'm even qualified to go into. But you'll see here in a minute, I'll give an example of the focality of MSP. But that's something that really sets SOURCERER apart, is the inclusion of that algorithm. So that's kind of SOURCERER's, I guess, undercarriage in a nutshell. I'm going to close this down and now give you kind of a demo of how to use SOURCERER. So this is Flow. Flow is our data management system, which is pretty cool to use. But basically, in order to get to SOURCERER, you have to go through Flow. Flow manages all of your data. It's a good place to kind of put all of your data files and organize them in a way that makes sense to you. But for our example today, what we're going to do is we're going to work with some spike data from a patient with epilepsy. This is Flow. There is here what you're seeing is a list of the experiments. Each one of these, no joke, is a different experiment or kind of funny little experiment we're using for testing that our lab is running. So in here, these are all organized by experiment name. And then you have a little description in case, you know, for our case, since we are a manufacturer and developer, we have a lot of descriptions that just say testing. You can see the owner of that experiment. The one we're going to work with today is this one right here. And you have a couple options with Flow. You can either look at all the files that are associated with the experiments. You can look at just the participants, show the collaborators on the experiment, or just edit the information about the experiment. But what I'll do is I'll just click on the experiment that I want to work with and then click Show Participants. And this is for just my example here, I only have one participant and their participant ID is SYK. When you add participants to Flow, it's very simple. You just select that button. You can enter their ID, first and last name. If you need that, you can obviously make it anonymous if you need to. But I want to pay your attention to this age category here. This is where you select the age that corresponds to the different atlas you're going to use for source estimation in SOURCERER. So again, we have these ranges here, 0 to 2, 2 to 9. Sorry, I said 8 earlier, but it's 2 to 9 and then 9 to 18. And then adult. The participant we're working with today is an adult, as you can see here. But you can add as many participants as you want. And then once a participant is added, you would go to Show Files and then add a file underneath your participant. And you don't have to just use Flow for source localization data. You can use Flow just to store data. So for example, as you'll see later in another experiment we have, we use Flow to store a bunch of the inter files or the interim files. So when you're processing EEG, a lot of times you'll have one file that's raw, and then you'll have one that is filtered and then segmented, you know, yada, 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 all the way down the line. You'll have like 12 or 13 files for one person. I use Flow as a way to organize all of those files. Maybe I'm not using all of them, but I want some record of them. I use Flow as a legitimate kind of cloud-based data management system. But to access your file, I've already uploaded one. I just look at my participant here. This is the one file I'm working with today. So this one is filtered, segmented, baseline corrected, you know, all the tags that we usually have when we go through processing. You have a few other options. Once you have your file uploaded, you can delete it, you can use some information, or you can download it onto your desktop. But to launch Sorcerer, what you need to do is go all the way to the far right, click on Workflow, and then you would select Sorcerer, and that's how you launch it. Or you can do a few other workflows. A couple of them are grayed out right now simply because we are still working on them. But I'm going to click on Sorcerer, and it'll automatically launch Sorcerer in another tab. And while this is going on, are there any questions so far? All right. So since my participant was deemed an adult, the reason this is churning its gears here is because it's going through and it's loading in the adult atlas and all the things that you saw when I first started the presentation. So it's done retrieving all that information from the server. You can see it's downloading KD trees and all things related with the leaf field matrix. And now it's finally loading everything in. Okay. So as you saw before, this is Sorcerer. So this is one of the default views. What I'm going to do is I'm going to go through some of these different selections you can make to kind of make your view more optimal. I understand not a lot of people are going to want to just work with the default view. You might want to change some things, but essentially this is the default. You get 2 3-dimensional views plus all the slices. These slices down here are X, Y, and Z. This is the actual 2-dimensional MRI of the atlas. And then all of the pretty colors here correspond to the different tissue types. So this yellow is the scalp, this purple is the skull, et cetera, et cetera. I think the cyan is cerebral spinal fluid. You can kind of play around with this. You can zoom in and out. You can rotate your 3-dimensional models around. You can take the 2-dimensional view and use it as just a MRI viewer. But over here on the left, there's surface visualization control. A lot of times what I'll do is I don't like these sensors to be visible. They don't really tell me much other than that I have the correct net selected, which is also something worth mentioning, is that Sorcerer automatically detects the net that was used or the web that was used in your EEG file. So for this one, it was a 256 EGI net, and that looks correct. What I'm going to do is I'm going to turn off the sensors just because they get in the way, and then you get a clean view of the scalp. And then there's these submenus here where you can change the opacity of these different surfaces. You can turn off the left side of the brain, the right side of the brain. You know, you can kind of mess around with it. So if I'm doing source estimation and I don't necessarily need to look at the scalp distribution, what I'll usually do is I'll turn off the scalp too. So I just have a brain. And then over here on the right, these are different default views that we have. So you can look at just a single slice in a very large view, if you like. And then there are some that are more relevant to doing source estimation. The main one for me that I'll usually use is a dual 3D plus BP. That stands for butterfly plot. You can actually see your EEG plus a flat map. And this is my typical view for source estimation. And what this has is it has the 2 3-dimensional views, but it has this flattened view of the cortical surface. So you can see all into the ridges and valleys here and see any sources that you might not be able to see once we do source estimation on the 3-dimensional brain. And then probably of most importance here is the EEG. in a butterfly plot view. This is how you're going to select your time. This is how you're going to look at whether you're centered on a peak or halfway up a peak, where you're at in your segment, and find the time point to actually do source estimation. Scale bar settings we'll get to later. You can take snapshots. There's a default snapshot button that you can take a picture, and it gives a nice high resolution or standard resolution image of what you're looking at. But what we'll do now is we'll move over to doing a source estimation on this participant. So what we have is spike data, and you can see here, this is a large spike that I am interested in performing source estimation on. Over on the left, you have a few different options. You have the category. So if you have multiple categories inside of your EEG file, you can toggle through them. For an ERP study, this would be your different categories. Say for instance, you'll see in a little bit, the N170 paradigm will have like an ERP for people looking at faces versus looking at characters. So you can select which category you want to perform source estimation on. Different segments. This is an average of many spikes, so there's only one segment. And then if you need to, you can look through the different channels. And if there is a bad channel, you can enter it in here and it'll interpolate. You can select the reference channel. We're doing source estimation on a file that is already average referenced. So this is pretty locked down. I wouldn't want to change this. And then you would pick your inverse solver. So again, your options for a standard source estimation are S-Loretta and Loretta, and then multiple sparse priors, or we just call it Bayesian prior. Spectral we wouldn't use today, but you could do a source localization of different frequency bands if you're interested in doing that. If you're using S-Loretta and Loretta, you would set your regularization constant. So EEG estimation is kind of an ill-posed problem, and then to kind of treat that ill-posed nature of the problem, you have to apply some sort of a regularization scheme, which comes in the form of a regularization parameter. So I don't want to get down in the weeds too far with it. If you're not familiar with regularization constants, you can just leave this alone at the default. But there are some ways you can determine your reg constant. You can use something like an L curve. There's several papers out there on how to use an L curve. Generally, the higher the regularization constant, the more regulated the data becomes, which may help with noise in the data. It is not an excuse to use noisy data, right? The same saying goes, garbage in, garbage out. You should be working with very clean data, or at least as clean as you can get it. But you can mitigate at least some of the noise, and I'm talking very minor noise, by manipulating this regularization constant. For me, I'm just going to keep it at the default. And then to find the point that you want to do source estimation on, you would either slide the time marker here, and then on the left there, you can, on the right, you can see this big red line moves in conjunction with me sliding this, or you can just type in the number you want. For me, 0 actually makes the most sense. It's somewhat centered on the peak, even if I do, I don't know, maybe -3. Get it off the peak a little bit. Go further. Let's go -6. There you go. Okay. One benefit of using Bayesian prior is that there is no regularization constant to set. So that might be a decent selling point on using Bayesian prior. One thing you can actually use to determine which algorithm you want to use as well is Are you looking for a focal source? Or is there the potential to have multiple sources that are somewhat diffuse? This is where some a priori judgments come from you as the scientist to make the determination of, do I want a very focal source, or do I want something that could potentially lead to finding multiple sources, or a source that's rather large and diffuse? It's really up to you. In my case, I know the resection of this participant. I know that they resected a very specific area. The source of this participant's epilepsy was a very small area. So I'm going to use Bayesian prior because it makes the most sense for my data. So I'm going to click compute. And again, feel free to interrupt or interject any sort of questions you have at any time.
Kyle, I have a question about the time it takes on the different inverse solvers. Is there a significant time difference between them?
So typically Loretta and S Loretta are going to be a little bit quicker. And this is all relative. Nothing takes forever. Like, what I mean is these are all done probably sub 1 minute. So S Loretta and Loretta will be done in just a few seconds, but Bayesian priors will take, closer to like 30 seconds or so, as you just saw. It's, there is a time difference, but I mean, relative to each other, there's a time difference, but in the grand scheme of things, we're talking a difference of like, 15 seconds.
Yeah, that's probably a huge improvement of of the kind of methods and computation that it's able to do is really fast.
Right. Yeah. I mean, when we were first working on this and we didn't optimize anything, it took a while. Meaning I think Bayesian prior was taking 5-10 minutes. But I think this instance here is posted on BEL's internal server. And it goes, I mean, it flies. It's pretty fast. I mean, 30 seconds to do this versus back in the day, it was, 5-10 minutes. It's a huge improvement. It's pretty quick. Okay, so this is done. What I'm going to do is mess around with some thresholding. So you can see kind of faintly, which we're going to change in a minute, some source. What we can do over here is go to our scale bar settings. And first of all, I am not a fan of purple for source estimation. I'm maybe a little old school. I like looking at red and yellow. So I'm going to change it hot. There's a few other options you can do. There's like green versus pink. There's this like kind of weird green versus brown. And then there's traditional hot, which is like white hot versus almost black cold. You'll pay attention to it being all orange right now. We're going to scale this back. So by default, the SOURCERER interface is going to scale all of your source estimations to the minimum and the maximum. And if you deselect that, you can manipulate your minimum and your maximum to kind of shut off some of this orange or stuff that's just sitting at 0. So if my maximum is negative 0.14, what I could do is just change this to like negative, oh, sorry, I should be on the other one. I can just change my threshold to about half of that. And cut out some of the tails. There we go. Maybe go a little bit further. Let some more in. So you can play with your thresholding to kind of cut out, and make a node if you need to look at your sources. For this particular subject, you can see that the source estimation is very focal. I've thresholded this very liberally, aggressively. I'm letting in more estimated activity than what's even worth. The actual focal min and max is like almost a pinpoint. But if I show you the actual resection of this person, let me get out of full screen. So this is the actual resection for this subject. On the right here in yellow, this is a drawing from the overseeing physician that performed the surgery on this subject. This is their drawing on the preoperative MRI, registered to our atlas, a drawing of the area that they resected. So you can see it's a pretty small area, but this matches pretty closely. If I were to look at just maximums, so if I go snap to maximum, you can see that the maximum value is within that resected area. So it's pretty accurate. One thing about SOURCERER as well is we give you MNI coordinates of the maximum. So if you just click snap to maximum, you can look at the flat map here. And then in the lower left, you can get your MNI coordinates and then the Brodmann areas. So this is fusiform gyrus. And then it shows you your gray matter. I would sure hope so. And then it tells you the intensity of the dipole along with the dipole number. This can be important if you are trying to export these values and run some form of statistic. And yeah, so that's kind of the basics of source estimation. I'm gonna swap to another file and show you, some more traditional ERP data and not just clinical like spike data. But for now, are there any questions at all? But either way, you can see how, it's pretty simple to use. You can play with your thresholding to make figures. As far as performing statistics, you can save the inverse solution if you'd like and get these values exported out. You can take snapshots. It gives you MNI coordinates in case you're trying to look at some standardized way of viewing the area that is estimating your sources. Quite a few things. The two-dimensional map is also nice to use. When we have individual models, this will be even more powerful because, say, for example, I have some sort of lesion. I'd be able to view it in the two-dimensional view and actually see whether the source estimation lines up with the lesion, just as an example. Okay, I'm going to swap to another participant and show you how easy it is to just kind of go from experiment to experiment. So I'm going to go from being a clinician to being a basic researcher. Just going to close this out. I'm going to show you some traditional ERP data. This is the N170 paradigm. Let me find it real quick. See, when you have a large lab with a bunch of people, your number of experiments is kind of insane here. So it is under N170 to support demo workflow. If I just show the files here. I want this one right here. While it's loading, I'll introduce you to N170. So the N170 is a ERP that reflects the neural processing of faces. amongst other things, like most ERPs. This particular paradigm is really well studied in the literature. It's used in different battery tests for recognition and memory, things like that. But the N170 paradigm, essentially, people sit in front of a screen and they will look at pictures of, in this case, I think it's a Chinese character. And then on some trials, it'll be a picture of a face. And the traditional way of looking at the N170 is you'll look at a component that's roughly 170 milliseconds after stimulus onset, and that component is largest for looking at faces when compared to something like a character or something inert. So if I go back to my favorite view, which is this one, on the left here, I can see my categories. So I have a character category, and then I have a face category. If you look at the butterfly plot as I swap between these, for the character, you can see that this is the N170 right here. You can see it's rather small, but it becomes much more organized and higher in amplitude. I mean, this is 10 microvolts here. It's 150% of the size of the character N170. It's much more uniform and much larger in amplitude. So this is the N170. The N170 is most of the time, at least from, it just depends on who you talk to. Obviously, there's rarely any consensus on this. Hopefully, SOURCERER helps sort some things out. But from like intracranial recordings, fusiform gyrus is thought to be one of the main producers or main sources of the N170. So we'll try to use SOURCERER here to go in and see if we can't localize it to fusiform. So you see our peak is about 200 milliseconds. I'm going to set it about halfway up the peak. And if you look at the cursor there on the butterfly plot, as I move my cursor along the signal, the first number is milliseconds after the stimulus. So it's 176 milliseconds. And then it gives you the amplitude, so negative 9.5 microvolts. And then the electrode that I'm actually clicking on here. But if you're trying to find an easy way to figure out where you should localize, you can always just use this as basically like a scroll bar, because you can't just drag this bar here, as of now at least. You kind of have to know where you want to put your bar, either by just scrolling it with the time marker on the left here, or a cheat way is to just go over here and say, all right, that's good, 178, and then type it in, 178. Just much faster. For this one, I'll just use SOURCERER. We'll kind of see how much of a time difference there is. Also, I don't think this needs to be particularly focal. I think given that the N170 can have multiple sources, it might be even a better idea to use something that's a little more diffuse, like SOURCERER. I click compute. So remember, Bayesian prior took maybe 20, 30 seconds to process. And, this one took maybe 5, 10 seconds. So it's, I mean, everything's relatively quick. Nothing takes forever here. But just looking at these, I mean, you can see we're pretty close to fusiform gyrus there. Yeah, I mean, we're close. We can threshold. Okay, not that intense, sorry. I get a little heavy-handed. Snap that to maximum. Temporal pull, so it's not actually fusiform gyrus. It's pretty close. I mean, for an atlas, it is pretty close. And if we're looking at the top 50% of activity, fusiform bilaterally is activated. If we look at the scalp, you can see the inversion line is where traditionally an N170 would be. We maybe have a bad channel here and there. But yeah, so you could take this, export it, run statistics if you'd like. You can just take pictures and do some sort of visual analysis. There's many things you can do, but you can kind of see how easy it is just to set up Sorcerer. Everything's fairly integrated, fairly quick. And I guess one thing to note is that it's pretty accurate, especially for just using atlases. Obviously, some of the errors of being less than a centimeter off, maybe a half centimeter from fusiform gyrus being the maximum. Once you switch to an individual head model, maybe that will cut down. But this is pretty accurate, pretty fast, very easy to use. And that's all I had for the workshop. I try to leave about 10-15 minutes for questions. So if there are any questions, I guess now would be like a perfect time to kind of open up the floor. If anyone has questions about Sorcerer in general, maybe not just like how to use it.
Yeah, Kyle, thank you so much for that presentation. I really like seeing all the different views and all the different visualization that you went through. And so just like a very basic general question about accessing Sorcerer. So you access it through Flow on your web browser.
Right. So actually Flow stays open when you do this, so I can even toggle back. So yeah, it's accessed in the browser. You'll just have a web address and some credentials to log into Flow, and then yeah, you access it from here.
That's great. So you could ostensibly access your data from not just one location.
That's right. Yeah. So you can either, I work from home.
Right. I was going to say, in the world of working from home, that makes a big difference.
Exactly. Yeah, I epitomize work from home. So yes, all this data is hosted. I think this is our on-premises server. I don't think this is Amazon Web Services. So I'm accessing data just by using VPN. This is all in-house at BEL. And then I think we have the opportunity to use AWS if people don't want an on-premises server. So yeah, it's all, and this is a Mac Mini, one of the new ones, which has a bunch of issues with compatibility with like MATLAB and all the other programs, unless you want to run Rosetta. So what's really cool is that, even newer machines that don't have a ton of support, I'm running this on a brand new machine that was just released, and absolutely no problems, because all it needs is Google Chrome. And it's not even like the fastest machine ever. It's like a glorified laptop, but runs fairly flawlessly.
Hey Kyle, this is a great demo. I have a question. Can you go back to the Sorcerer interface? So let's say if I have a bad channel, if we look at the visual, the top, if I see there is a bad channel, how do I remove that bad channel?
So there's a couple ways you can do it. In this case, so if I remove the sensors, you can see I have this little pock mark here. What I could do is I can see that it's pretty obvious that it's electrode 232, which if I go down my butterfly plot, I can also confirm that 232 is way off the baseline.
Yes.
I would type in to bad channels 232 and enter it, and then it gets automatically interpolated. And then if I turn off the sensors again, you can now see that pock mark is removed.
Cool.
So,
and in this case, I see that button changed to compute, meaning that you need to recalculate the source localization after making the mark bad channel.
Yep. Yeah, so as soon as you do that, it actually clears source space, so you can see that there's nothing. And that's just kind of your reminder that you need to recompute given this new signal.
Yeah, cool. This is very intuitive.
Yeah, and then you'd obviously have to re-threshold.
Yeah.
But yeah, it's kind of a nice little reminder. I mean, because all the time I'll do source estimation, be like, oh, that really doesn't make any sense, and I'll go back and find a bad channel. And then, you know, instead of just trusting the result that's still on the screen, because I mean, it updates automatically. As soon as you enter in a bad channel, you'll see your butterfly plot move, but then you'll go back. And in other source estimation softwares, I mean, this is not something that's super unique to SOURCERER as far as like changing bad channels on the fly in the user interface. But in the other ones, it leaves your source space up, giving the illusion that everything has been updated. And then, I mean, there's been a couple times where I've taken a screenshot and or exported statistics of source space, and that's going to trip me up. So this is a nice one that just kind of clears it, and there's really nothing you can do regarding source space if you touch a channel until you recompute and ensure that everything's up to date.
And this data is, I noticed that this is a EGI data, right?
Correct. Yeah. So this is
the one thing that's also very helpful, because you know, SOURCERER supports not just the BEL data; it's actually fully compatible with the EGI data also. Right.
Yeah. So when I made these atlases, I think so. I support 32 channel, 64, 128, and 256 EGI data. So remember when I made the atlases, I had to make one for each one of those nets, which was rather tedious. But so we did 32 through 256, and then obviously there's all BEL's head webs.
Great, thank you.
Yeah, of course.
Yeah, Kyle, thanks for a great demo. And I think if anyone has any other questions, go ahead and ask it now. I think this has been like a really great presentation for SOURCERER. And if there are no other questions, we'll go ahead and wrap up.
Cool. One thing I wanted to do real quick. How do I get to chat? Here we go.
Oh, Mariana's paper.
Yeah, there's his paper. So just type it in there. Whoops, sorry, that's to just you. There you go. So there's the title, and then there's the actual link to the Science Direct paper, Elsevier. I believe this one's open source, so you can just read it without having to pay $1 million. But yeah, so that's everything I had.
Thanks, everybody. Thanks for participating today.